All right, everyone. So we're going to be looking at lesson 4, and really quickly, we just kind of want to review enthalpy and endo and exothermic reaction. Remember, energy is a reactant. Energy is being used and absorbed mostly, so you would see it kind of like A plus B plus, let's say, 50 joules of energy producing C and D as our products. Okay, so we have heat energy right here as a reactant. Whereas in an exothermic reaction, it's the opposite. Energy is a product. So if we flip this and C and D are the reactants, then you have A plus B plus 50 joules of energy. Now, when we look at the change in that enthalpy, okay, because the delta H for a reactant, this would be positive 50 joules, but delta H for as a product, that's a negative 50 joules because it's on the product side and it's being released. However, it doesn't have the negative sign in the equation. The negative tells you that it's a product being released. So when we look at the change in enthalpy, this is the overall change in the bond energy of a reaction. Okay, it's the overall change in the bond energy. Which, remember, that bond energy, that's the potential energy that is stored in the bonds of the molecules. And so the formula for this is that the delta H of our reaction, so the change in that bond energy, is equal to the change in energy of my products minus the change in the bond energy of my reactants. So we've looked at this with the endothermic and exothermic graphs, but you can also see that data through a chemical reaction if you're given standard values of delta H. So these values here for delta H are in kilojoules per mole. And these numbers all come from a reference book. So these are just known values that would have to be given to you for this sort of thing. Now, this tells us that it's kilojoules per mole, so that's 1 mole. Now, keep in mind that in your chemical equation, we have moles right here in our coefficients. Okay, so the 2, the 5, the 4, the 2, these are the number of moles of that chemical that get used in this reaction. That's where we get our mole ratio from in stoichiometry. And so to calculate the delta H of our reaction, okay, because they want to know the change in enthalpy of the reaction and to identify if it is exothermic or endothermic. So what we first do is identify our reactants and products. So I'm going to highlight my reactants in yellow. That's the C2H2 and the O2 on the left side of my arrow. And so what we see here is that the delta H of my reactants, which this R is going to stand for reactants, is going to be equal to those things combined. Now, if we look, C2H2 is 227 kilojoules for every 1 mole. But in my equation, I have 2 moles. So this means we're going to take our 2 moles of our chemical and multiply it by 227 kilojoules per mole. And just like in our equation, we're going to add it to oxygen's value. Well, oxygen has 5 moles in our equation, and it's worth 0 kilojoules per mole. So multiplying by 0 kilojoules per mole is going to make our life easy. We know that this 5 times 0 is just 0, okay? So it disappears. On the C2H2 side, we have moles cancel out with moles, and this tells us that the delta H of our reactants is going to be equal to 2 times 227, which is 454 kilojoules. Okay, so that's how we find out the delta H of our reactants. Now, we're going to need to do the same thing for the product side. The product side has 4 moles of carbon dioxide, so 4 times negative 393.5 kilojoules per mole. Oh, I forgot to write moles here. Okay, plus the 2 moles of water, so 2 moles times negative 241.8 kilojoules per mole. When I look at my units, moles cancel out with moles, moles cancel out with moles. 4 times negative 393.5 gives me negative 1,574 kilojoules plus 2 times negative 241.8 is a negative 483.6 kilojoules. So that tells me that my delta H of my products is negative 1,574 plus a negative 483.6, which is negative 2,057.6 kilojoules. Now, one thing we'll notice is that in this reaction, energy is being absorbed because it's positive. It's also being released because this value is negative. However, the releasing is much more larger number than the reactants. So what we'll notice is that when we do the delta H of our reaction, which is the delta H of my products minus the delta H of my reactants, that will give me a very interesting value. We'll have negative 2,057.6 kilojoules minus 454 kilojoules. And that tells us, let's see, negative 2,057.6 minus 454 gives us a negative 2,511.6 kilojoules. So this is the delta H of my reaction, and because that is negative, it's being released, which makes this an exothermic reaction. Okay, so when you do this, you just take your coefficients, okay? That was the number of moles that we are multiplying by. And we use that and multiply by the number on the chart, and then products minus reactants. So that's the first part, just kind of reviewing. Now let's look at heating and cooling curves. One thing you'll notice on a heating and cooling curve is temperature is on our x-axis. So if the temperature is going up, then it's a heating curve. If the temperature is going down over time, it's a cooling curve. So you'll notice that this graph here, this light blue line, is going to be our cooling curve because over time from left to right, the temperature goes down, whereas this curve is a heating curve. The dark blue one is increasing in temperature as we go on. So when you have a heating and cooling curve, it's going to show your phases of matter. Okay, and so we're going to look at what the different types of lines refer to, but you're going to need to actually be able to write on the graph. So on a heating curve, this first segment here, okay, this is where your substance is a solid. So we're specifically looking at water. So this is for good old H2O. So here you have ice, which is a solid. So this is H2O as a solid, okay? And here, this, and that is also, no. We have a solid, okay? And what happens is it begins to melt, okay? And then once it melts at 0 degrees Celsius, it will become a liquid, okay? So you have water is a liquid, and that liquid will continue to heat up and heat up and heat up until it reaches 100 degrees. This temperature right here is our boiling point, okay? And this is where you're going to have vaporization occur. So with vaporization, that could be evaporation or that could be boiling. Both are part of vaporization. And then after every single thing is evaporated, it is all 100% a gas. So right about here in the middle of this, you're going to have half liquid and about half vapor or gas. So really keep in mind that time and the amount of heat is going to determine the ratio of that. With the cooling curve, you're starting off at a high temperature, so that means you're starting off at a gas. You're condensing once you get to that boiling point, except you're reversing it. Then you still have a liquid. Then you begin to freeze and you get a solid. Okay. So one thing that we want to really look at is that when you see those flat lines, okay, this flat line represent your phase changes. Okay. This is where your phase changes occur. And that means energy is used to either break or create the intermolecular forces. Okay? Remember, these are the forces that hold multiple molecules together. Okay? They're used to break or create those intermolecular forces. Now, when you're heating up, you're going to be breaking the forces, and when you're cooling down, you're going to be creating those forces. The slanted lines are when you have heating or cooling going on, and that means the energy is being used to either speed up when it's heating or slow down when it's cooling the atoms, okay? So energy is used for one of two things. It's either being used to break or create the intermolecular forces, or it's being used to speed up or slow down the atoms, okay? And so on the back, you're going to have some practice problems with delta H, but you're going to have some practice with these heating and cooling curves as you look at what is happening at each point along the curve. So this is the main goal of your lesson, is to just use these to be able to answer these questions. So really take a look at that.